Okay, this is section 7.2, law of cosines. So then this section, you will use law of cosines, and those formulas are given right here, and they're also on your green sheet. So this first slide here is just showing you basically the formulas. Again, they're on your green sheet, and you will use law of cosines when you have one of these cases, and they are side angle sides. So when you have the two sides on the triangle and you know these angle sizes of the angle between them, the side angle side, and when you know all three sides. So those are two times you can use law of cosines. Here's the formulas. So there's one if you're trying to find side A, one if you're trying to find side B, and one if you're trying to find side C. They're pretty easy to remember, but you don't have to because they're on your green sheet. But the side you're trying to find of the three sides is on the left. The other two sides are squared and added, and then you're subtracting 2 times these two sides, the product of these two sides. So it's kind of easy to remember. And then this is always the angle times the cosine of the angle that's opposite the side you're trying to find. So these will always match. So, for example, if I covered that up, it's pretty easy to, if B is the side I'm trying to find, then this is going to be A squared plus C squared minus 2AC. Cosine of B, always angle across from the side. C squared equals A squared plus B squared, the other two sides, minus 2AB, and then cosine of C, because C is the angle across from side C. So that's, and you can also, if you happen to know all three sides, if it was a side case, you would know side A, side B, side C, then we would be able to find angle A. So we would know everything but the angle. And I'm not sure on your formula sheet if they just give you the formula this way, or if they also give you the, with it solved for cosine A, cosine B, and cosine C. I will have to check and see, and I just don't remember off the top of my head if they're given both ways. But either way, it's just you got to do a little bit of algebra if they give you A, B, and C, and you're trying to solve for angle A. So, all right, let's jump in and try an example where we use law of cosines to find some missing parts on the triangle. So, all right, so in example 1, we have a triangle. On this triangle, it has, we're given, let me just draw the triangle up here. We're given, let's call this A, B, C. So I'm given angle A, this is 48 degrees. I'm given side B is 15 inches. And I'm given side C is 25 inches. All right, so I have to find side A, I've got to find angle B, and I've got to find angle C. So let's start with the one side and we'll finish up the side. So if I'm looking for side A, so remember the formula means the A is the side I'm trying to find, so I go with the one that's got the A over here. So the other two are, the other two sides, it's going to be B squared plus C squared minus 2BC cosine of angle A, so times the cosine of angle A. All right, so let me fill in what I know. So I know, I don't know A, that's what I'm trying to find. I know B is 15 squared, and C squared is 25, minus 2 times 15 times 25, and then, times the cosine of 48 degrees. All right, and so I can literally just go to my calculator and type this in, and I'll get what A squared equals. So A squared equals, so I think I have this in Desmos because I did it just, no, I don't either. Okay, so let me delete this out. All right, so it will be 15 squared plus 25 squared minus 2 times 15 times 25 times the cosine of 48 degrees. All right, I want to make sure I'm in degree mode because otherwise it's going to read that as 48 radians. Don't want that. All right, and so Oh, again, I think this is some left over from before needs to go. 15 squared plus 25 squared minus 2 times 15. Not sure what the problem with this is. Well, I don't know what happened to that, but it's not liking it. Let me go up here. Maybe it didn't like having the. There we go. 348.15. 348.15. And then A will be the square root of 348.15, which would be okay, calculator on here. 348.15 square root of that. It's 18.7 roughly. So in keeping with significant digits, let's keep it 2 to significant digits. Let's just round it up to 19 inches. All right, so side A is found. Now, to find the angles, well, finding one angle is all I have to do, because then I would be able to use the 180-degree rule to find the other. So let's just pick one of the angles and find it. So I can do B or C, it doesn't matter. I'll just do B. I'll do C, so I marked it there. So now if you were solving for C, C squared equals A squared plus B squared minus 2AB times the cosine of angle C. So I could go ahead and plug the values in, or I could go ahead and just solve this for cosine of C. And I think, if I'm not mistaken, they're on your formula sheet given to you that way, so you wouldn't even have to do this work that I'm doing right now. But it's a good way to show you where those formulas come from anyway. So let's solve this for cosine of C, because this is what I'm trying to find as angle C. So let me just isolate cosine C. So I'm going to subtract the A squared and the B squared over to the other side. So I'll have C squared minus A squared minus B squared equals negative 2AB cosine of angle C. So these are subtracted out. Now they're over here. And then I've got this. Okay. Let's divide both sides by negative 2AB. All right, and that all divides out, and I have, so basically the cosine of angle C is C squared minus A squared minus B squared divided by negative 2AB. So now let me go ahead and plug my values in. So C is 25, so 25 squared minus A, which is 19 squared, minus B, which is 15 squared, and that's going to be divided by negative 2 times A, 19, times B, 15. All right, so let me type this into my calculator, and I'll just go back to Desmos and use that. All right, so 25 squared minus 19 squared minus 15 squared. That's divided by negative 2 times 19 times 15. All right, so I get negative 0.0684. negative 0.0684. All right, so now we know, how do you find C, angle C? Well, we have to inverse cosine, and we have to inverse cosine to find the angle. So let me go back to Desmos, and I will inverse cosine of that value. So let's just inverse cosine of this whole thing since it's already in there. Okay. So it looks like it's going to be 94 degrees. So angle C would be 94 degrees. All right. Now remember cosine, let me just address this issue right here. So if you're thinking, well, all right, 94 degrees is right here in quadrant 2. Cosine is also negative down here. And so if you had, if this was 94 degrees, 180 minus 94 would leave this being 86 degree reference angle. And then that means this would be 86. So just to verify that 180 plus 86 is way too big to be an angle in a triangle. So I don't have to worry about the other angle here. It's not possible because it's bigger than my 180 degrees, which is all three angles in the triangle. So the only angle that I could have that's 94 would be this one, just one of them. I can't have an angle this angle is not going to be able to be in this triangle. So normally we're interested in, all the angles that could have a cosine of negative 0.0684. But in the context of this problem, it doesn't make sense to have an angle that's 180 plus 86. So we rule that one out. So this angle is 94. Now, finding angle B is just, I can use the fact that I know there's 180 degrees in the triangle. So if you add 94 and 48, that adds to 142. And that means that the missing angle B is 180 minus 142, which is going to be 38 degrees. All right, and that solves the triangle. We have all three angles and all three sides, and we are done. All right, let's look at another one. All right, now this one, it doesn't just give you a triangle directly. So it says the diagonals of a parallelogram. So remember a parallelogram, let me draw that up here. So a parallelogram has the quadrilateral in which opposite sides are parallel. Going back to geometry here. The diagonals of a parallelogram have a length of 28.2 centimeters. So let me draw that one in, and I really missed that bad. It's not really easy to use. So, okay, let's try this way. Oh well. And this diagonal is, okay, so we get the diagonal. So the longer one will be 28.2, the longer one will be 36.4, and the shorter one will be 28.2. They intersect at an angle of 60.4 degrees. So this angle is obviously bigger than 60.4, so I'm going to go in here and put the smaller angle to be that. So that's this angle right in there. Now, one thing we know, if you remember from geometry, if you have a parallelogram, the diagonals bisect each other. So what I know is if this whole diagonal is 28.2, this is 14.1, and this is 14.1. And this is 36.4, this is 18.2, so it splits it in half. This is 18.2. So the task is to find the shorter side of the parallelogram. The shorter side of the parallelogram, let me label, is this side right here, or this side right here, it didn't matter. So let's just focus on the triangle we have. So this is 60.4. So I know, let me just pull that triangle out now. So I know that I've got this triangle here with this angle being 60.4. Let me just label this A, B, C. The side across from that angle at 60.4 is my unknown, so it will be A instead of X. And so the other two sides of the triangle are 14.1 and 18.2. Okay, and that's another side angle side case. I'll just be trying to find side A if I know side B, side C, and angle A. So A squared equals b squared plus c squared minus 2bc times cosine of angle A. All right, let me fill in what I know. I know B, say is 18.2. We know C, 14.1 minus 2 times 18.2 times 14.1 times the cosine of angle A, which is 60.4. All right, now I just need to go to Desmos and type all this in, or my calculator of choice. So 18.2, if I remember all the sides, 18.2 plus 14.1 minus 2 times 18.2 times 14.1 times the cosine of angle 60.4, if I remember degrees, if I remember right. And I'm in degree mode. I want to make sure. Yes. All right, so I get 276.5. So the square, A squared is 276.5. 276.5. And so A is equal to the square root of 276.5, and the square root of that is 16.6. And that is the side, the short side of the parallelogram. Okay. Example 3. Solve the triangle. That means I've got to find all the other 3 parts. So let me draw the triangle here. So draw a triangle. So I'm going to label this A, B, and C. So A is given 26 kilometers, B is given as 19 kilometers, and C is given as 15 kilometers. All right, so in this case, we know all 3 sides. We do not know any angles. So we're going to start and find an angle, and then we'll probably have to go through and find 2 angles, and then use the 180-degree rule to find the third. Or after you find the first angle, you technically could use law of sines. That's another option that you have. So let's pick an angle. Let's just start with angle A. So if I'm trying to find angle A, so remember it's A squared equals B squared plus C squared minus 2BC cosine A. So remember when I solved this, I subtracted the B squared and C squared over, so I had A squared minus B squared minus C squared equals negative 2BC cosine A. And then I divided both sides by negative 2BC divided by negative 2BC over here. And so cosine of A, so cosine A is equal to A squared minus B squared minus C squared divided by negative 2BC. Now, again, if this is on your formula sheet, you're not going to go through this every time. You're just going to pull the one with the angle that you're trying to find. All right, let's see what I know. I know everything but angle A that I need. So I've got side A is 26. So I'm going to start with 26 squared minus 19 squared minus 15 squared divided by negative 2 times 19 times 15. And that's cosine of angle A is going to equal. So cosine of angle A, and then I need to go to my calculator and calculate that. 26, 19, 15. Okay, and then it's divided by negative 2 times 19 times, oops. All right, and I get negative 0.1579. Negative 0.1579. Let me double check and make sure I didn't. 1979. Oh, no, 1579. Glad I checked it. 1579. So let me fix that. Okay. 1.1579 negative. Okay. All right, so now we're ready to find the inverse, and so angle A is going to be the inverse cosine of negative 0.1579. So let's go back to the calculator and let's inverse cosine this whole deal right here. So let's inverse cosine of that, and I get 99 degrees. Okay, so A is 99 degrees. Now I'm going to have to do that one more time. And once I get that second angle, then I'll be able to just do the 180-degree rule. So I can pick B or C. So let me just go ahead and do B since we'll just go in order A, B. So this time, if you can kind of see how this works right here, this is when you're looking for cosine of A. And again, if it's on your formula sheet, then you don't have to worry about it. But if you have cosine of B, you take the B squared equals A squared plus C squared minus 2AC cosine B formula, and you solve it for cosine B, it's going to look like this. It's going to say B squared minus A squared minus C squared divided by negative 2AC, and then we just plug in chug here. So cosine of angle B is going to equal B, which is 19 squared, minus A squared, which is 26 squared, minus C squared, which is 15 squared, minus 2 times A, which is 26, times C, which is 15. All right, so 19, 26, 15. Okay, and then on the bottom, I need it to be negative 2 times 26 times 15. All right, and I've already got the inverse cosine in front of that, so this is actually my final angle. So the angle measure is 46 degrees, and that was angle B. So 46 degrees. Now, angle C, of course, is 99 plus 46 is 145. 145 minus 180 is 35 degrees. So just using the 180 degree rule gives me that. So side angle A is 99 degrees. Angle B is 46 degrees, and angle C is 35 degrees. And that solves the triangle. Okay, the next slide contains some things you'll see this in the notes as well, that you're going to have some problems, some application problems with log cosines that deal with navigation, ships, planes, that kind of thing. And so you're going to hear two different terms that are very similar, but the heading and the true course, and we also had dealt with bearings before, so a little different with these. But so basically, the difference between a heading and true course. So a heading is the angle measured clockwise from due north. So basically, let's say I have a boat or plane or whatever, and let's say it's heading this direction right here. So the heading, this is due north. So the heading would be this angle measured clockwise from due north. So clockwise goes this way from due north to the vector representing the intended path of the object. So this is the intended path. This is the way they mean to go. Now, why would there be a true course? Why would this not be the true course? Why would they intend to go this way? Why would they not go this way? Well, there's other variables that could act on that plane or on that ship and throw it off of its intended course. For example, wind, current, things like that. So the true course of an object is the angle measured clockwise from due north. So they're both measured the same way, but to the vector representing the actual path. So the difference in these two is one is the actual path. The true course is its actual path, and the heading is the intended path. So let's say that it might intend to go a plane flying. Say it may intend to fly this way, but there may be wind that is pushing it down, and this might be the intended path. This might be the actual path. So this would be measuring the actual. So this would be actual, and this would be intended path. So that's the difference in those two. So mainly when they're talking about heading, it's just, where they intend to go. That vector that represents where they intend to go. True course means where they're actually going. So there's something acting on them that probably is throwing them off of their intended path. But they're measured the same way. You measure them measure them clockwise from due north. Okay, this is just a little more explanation on this next slide of this navigational language. So this one says the figure below shows two vectors that represent the velocities of two ships, one traveling 14 miles per hour in the direction 120 degrees due north, 120 degrees from due north. So its path is at 14 miles per hour, which would be the magnitude of that vector. It is traveling, so 120 degrees right there. And then the other one is traveling 12 miles per hour. That's the magnitude of that vector at 240 degrees from due north. So you would measure its course from here, from due north, around 240 degrees. It says, note that although a boat is headed in one direction, its actual path may, I skipped a sentence there, to give the path of the ship traveling 14 miles per hour using the bearing method, we would say it's on a course of bearing. Remember how bearings go. I read that 60 degrees east of south is how I read it. So that means that where do they get that? Well, this we're looking at the path of the ship right here. So it is, here's south. So it is traveling. And this is south, this is east, and this is west. So we would say this angle in here is 60 degrees because 180, that's 180 minus 120 leaves 60. So we would give the bearing method as saying it's 60 degrees east of south. So from here south, it's to the east of south by 60 degrees. That's the bearing method. All right, so let me go on to the next sentence. So note that although a boat is headed in one direction, its actual path may be in a different direction because of the current of the river. The same thing can happen with the plane if the air currents are in a direction different than that of the plane. So the wind can slow you down, it can throw you off course, it can speed you up. With headings, the angle is measured from due north to the intended path of the object, meaning the path if it were not affected by the current or wind. The true course is the angle measured from due north, which is what we just said, to the actual path traveled by the object relative to the ground. If there is no exterior forces, no wind, no air, anything like that, then the two courses should be the same. So your true course and your heading should be the same if there's no other forces acting on the object. Okay. All right, so here, this example 4 is a navigation problem. So we have a plane flying with an airspeed of 205 miles per hour with a heading of 105 degrees. So remember heading, what that means. That is the direction it's intending to head. So let me draw this so far. So the heading, so this is due north. So if the heading is, make this so long. If the heading is 105 degrees, that means 105 degrees clockwise from north. So 90 is here, so let's make it kind of, this plane's intending to fly this direction right here. That's 105 degrees. All right, so that's the heading. All right, so it's flying along, and the length of the vector is represented by the magnitude of the vector, we say, is represented by the 205 miles per hour. So it's going 205. I'll come back and label those in a second. I don't get too much bunched up in here. All right, then we have the wind currents are running at a constant 35 miles per hour at 155 degrees clockwise from north. So again, the wind is coming in at 155, so this is north. There. So the wind is acting on it, so 155 degrees. Let's kind of estimate where that would be. So that's 155 degrees. So what happens is this might be the intended path, the heading, but the actual path is going to be the resultant vector here. So we would say if this is vector v and this is vector w, this would be v plus w, would be the sum of the two vectors. And I know we haven't done much with vectors, that's why I'm not real sure why we don't have a little bit more of that before we jump in to do some of these kind of word problems. But it's the law of cosines is that part of it. It's not necessary to know any of this, but if you get into some of these word problems, it's gonna take a little practice on getting how to draw these out and how to set them up. So remember that, let me label the magnitudes of these vectors. So this is the plane flying at 205 miles per hour. That's the length of that vector that represents the plane's path. And then the length of the wind vector that represents the speed of the wind is 35 miles per hour. All right, so we're asked to find the true course, which is this. So the true course would actually be this angle right here. So to get the true course, I'm going to need to know this little angle right in there. And the ground speed. So the ground speed is going to be the length of this vector. So let me label this triangle just to make it easy to name these. I'll call this A, B, and C. So I will need to know little c, and then I will need angle angle A, so I can add it to 105 to get the actual true course of the plane. So let's start with finding the magnitude of the resultant vector here, which is c. That's going to tell me the actual ground speed of the plane. All right, so I have basically got these two sides. Now I do know a little geometry here. So this angle, the blue angle right in here is 105. I will need to use something from geometry. I can find this angle right in here. So if you are a little rusty on your geometry, think about, when you have two lines and a transversal, remember those special kinds of angles. If you remember what the relationship is between these kinds of angles right here, those are called same side interior angles, or some text column consecutive interior. But the bottom line is they always are supplementary. They add up to 180. So these two angles here have to add up to 180. And that's just something from geometry that you'd have to remember. So this is 105. This angle has to be 75 because 75 and 105 is 180. Now, what does that do for me? Well, if this is 75, this is 155. 75 plus 155 is 130. So that's 230. Yeah, 230. So these two from here around to here is 230. Well, it's 360 all the way around. So I can figure out now this angle in the triangle by taking 360 minus 230. So if I subtracted 360 minus 230, I get 130. And that's going to be the measure of, that gives me one of the angles in the triangle, which is going to be helpful. So I got that angle. So now I've got the case of side, angle, side. And now I can find my opposite side. So if I want to find C, go to your formulas. Then I have to know A and B, which I do. And I need the angle C, which I now know. So I'm just going to plug those values in. All right, so A is 35. B is 205. And angle C is 130. So times the cosine of 130. And then I will go C, of course, is going to be the square root of all that. I'm just going to do that. All right, and then let's see what we get. 35, 205, and 130 is the angle. I already got it in there because I had actually done that. Okay, so this is where I calculated it. 35 squared plus 205 squared minus 2 times 35 times 205, cosine of 130. All right, and then I need the square root of that. So square root of 52474. point 229. So that is the ground speed of my plane. That is the length of the magnitude or the length of the resultant vector here. So this is, we'll round it up just to keep significant digits to 3, 229. So C is 229. So that's part of the question. It asked me to find the ground speed of the plane. So we knew the speed of the plane in the air. We knew the wind speed. And so if, all right, so now I need to find the true course, so which is this path right here. And so I need this angle A to be able to answer that. And I'll add that to 105 to get the how many degrees clockwise from north that the true path is. All right, so I need to find the angle A. And actually, I can do law of cosines, but I can also just do law of sines. So sometimes most people like law of sines. It's a lot easier to remember. The formulas are a little simpler. So, if you can use it, if you got the information that you need, and we do to use it, by all means, if you can prefer it, do it. And that's what I'm going to do. So I'm going to say 35 over the sine. So it's basically A over the sine of angle A. This is what I'm trying to find. Don't know. Equals, I don't know B, so angle B, so I can't do that, but I do know this one. So 229 C over the sine of angle C. And that angle was 130. All right, so just to clarify what I did there. So I had enough information to be able to use law of sine. So I had 35 over the sine of angle A, which is what I'm trying to find. This is my unknown, equals 229 over the sine of 130. And then I can cross multiply and solve that. So I'm going to have 35 times the sine of 130. Fix that. Equals 229 sine A. All right, and then I'll divide by 229. All right, so I'm going to have sine of A, and so I'm going to have to find angle A. I'm going to have to inverse sine both sides. So inverse sine of all this is going to be what angle A is. So A is going to equal. So let me go to my calculator now. 35 sine of 130. So let me go ahead and just do inverse sine 35 times the sine of 130 in degrees, which is what I want to be in. And that is divided by 229. Oops. All right, 6.7 is the measure of that angle. So now this little angle in here is 6.7 degrees. So the heading, or I'm sorry, the true course is how many degrees clockwise from north the actual path is. So it's 105 plus 6.7. So 105 plus 6.7 degrees is going to be 111.7 degrees. So again, to keep in significant digits, let's just round that to 112. So the true course is 112 degrees. So I found both things, the ground speed of the plane and the true course, which is just how many degrees the actual course of the plane is with the wind acting on it, clockwise from due north. All right, our last example. This one actually is pretty easy to draw out and to solve. All right, so we have two planes that leave an airport at the same time. Their speeds are 130 miles per hour and 150 miles per hour, and the angle between their courses is 36 degrees. So let's look at what we know. All right, so this time they leave an airport. So let's say here's our airport. So we know that the angle between their courses is 36 degrees. So let's just make it like, fix that. Okay. So, all right, so 36 degrees. Now one's going faster than the other, so it's going to cover more ground, or more air, I should say, than the other one. So we'll say this one is traveling 130 miles per hour, and this one is traveling 150 miles per hour. So the question is, how far apart are they after an hour and a half? So how far apart they are is this distance right here. Now, we don't know the distances here and here. It's not asking me it's not asking me for their speed or anything. It's asking me the distance they're apart. So remember that distance is equal to rate times time. So if they tell me that they're going 150 miles per hour, 150 miles per hour, how much distance is that in an hour and a half? So basically that's going to be 150 times 1 is 150 plus half, 0.5 times 150 is 75. So 150 and 75 is 225. So it's trying to not use a calculator. And that would be miles. So if you do 150 times 1.5, that's 225. So this times 1.5 hours means their distance was 225 miles. So this vector represents a distance of 225 miles. All right, since they're traveling the same amount of time, this guy is traveling 1.5 hours also, and 130 times 1.5 is 130, and then half of 130 would be 65. So 130 and 65 is 195. All right, so just a quick way to do 130 times 1.5. So this is 195 miles would be the length of this vector. Now, all we want to know is what is the length of this vector. So let me label my triangle A, B, C, and it doesn't matter how you label them. I just want to, it just makes it easier for me to name them as I'm talking about them. So I would be trying to find side C in this case. So let's do the law of cosines to do that. So again, it's a case of side, angle, side. You couldn't do law of sines if you tried to. You could have C over the sine of 36 equals 195. I can't have two unknowns. I don't know that one. I can't do this one either because I don't know the angles. So I have to use law of cosines. All right, so I'm trying to find side C, so I'm going to go C squared equals A squared plus B squared minus 2AB cosine C. Fill in what you know. A is 225 squared. B is 195. Also has to be squared. Minus 2 times 225 times 195 times the cosine of angle C, and angle C is 36 degrees. All right, and so I just need, then I can square root both sides, and I will get C to be, all right, let's go plug all that in. So 225, 195, and 36 degrees. Just go ahead and put it under square root, make it easier. $36. Always make sure you're in degree mode if you need to be. All right, so it's 132.9. All right, so depending on where they ask you to round, it doesn't specify. So, all right, and that's how far apart they are. They're 132.9 miles apart, and that's all it asked on this question. So that one was pretty simple. The only trick to that one was you had to realize that they're giving you the speed, and you want to know how far apart. You want the distance they're apart, so you need the distance of each one of these sides. So I had to use since I knew in an hour, if they go 130 miles in an hour, they go 195 in an hour and a half. If they go 150 in an hour, they go 225 in an hour and a half. That was really the only trick to that one. All right, so that is law of cosines. So it's just really using those formulas in cases where you know two sides in the included angle, or when you know all three sides, you're able to use it to find the angles.